Welcome, everyone. My name is Rich Collins. I'm Senior Director of Product Management for the ARC-V portfolio at Synopsys. And today we're going to talk a little bit about some of the things that we're doing to enhance the standard and our implementations around real-time application performance. So I'll talk a little bit about the background. A lot of the real-time activity that we're working on is largely directed by our activity in the automotive space. Of course, real-time applications are not just automotive, but that is one of the areas where there's a pretty significant need for real-time determinism in the processor portfolio. And then I'll talk about a couple of the things that we're recommending as enhancements to the existing AIA or the standard interrupt architecture, specifically to support real-time applications. And then we talk a little bit about kind of the results that we've seen and the things that we're recommending. So looking at the kinds of applications that require that real-time determinism, when we say real-time determinism, having fixed, understandable latencies, and the interrupt architecture is one of those areas where it's really important to have a handle on what that latency will be, basically the time it takes for you to get to that first instruction in the interrupt handler. And you look at applications like embedded vision, where you have to have the ability in real time to be able to determine what it is that, the objects that you're seeing in your field of view for the car, and obviously make a decision quickly on what needs to be done with the vehicle, especially as we move toward, autonomous driving in sort of the more mainstream. Radar, LiDAR, similar. In addition to the camera activity, if I have radar, LiDAR to, in bad weather, where I'm using that to enhance my ability to determine what's happening for blind spot detection, collision avoidance systems, things like that, that also needs to have support for real-time determinism. And then in general, passenger safety. This is all critical for both the passengers and the drivers in the car. So anti-lock braking systems, adaptive cruise control, making sure that the car stays the correct distance and it can brake in time if need be, things like that. All of these need to have real-time determinism in the processing for the chips that support the applications. So one thing that's nice about RISC-V as a standard, it's very scalable. So it can scale across a lot of different applications, whether you're talking about small microcontrollers for body electronics up to a full-blown multi-processor ADAS system that you would see, for instance, in a zonal controller and as vehicle architectures emerge. And the nice thing about that is that then software components can be redeployed. So if you have, for instance, a keyless entry system and you have a software module that's written for that, as you incorporate more functionality into a larger, sort of more encompassing device, that software can actually be ported as is, reducing the time that it takes to retest things. And of course, reuse is really important as these things try to get to market. And so the RISC-V ISA supports all of this, going from small controller types of cores all the way up to even server grade class of cores. But the nice thing that we found on top of that scalability of the standard itself is the ability to extend the architecture by being able to add specialized instructions, custom implementations, whatnot, to be able to enhance the ISA itself, enhance the implementations that you're building. And that's largely what we've taken advantage of for these real-time interrupt enhancements. So if you look more specifically about AIA, the interrupt ISA itself, there are lots of things that were done very well in terms of the general ability and support from multi-core configurations, virtualization. Again, this idea of being able to run virtualized workloads is all supported within the baseline interrupt architecture. Interrupts between processors in a system, the unified programming model, all these things were done very well in the existing AIA standard. But what we found is kind of missing is this extension of real time. So being able to support nested vectored interrupts, the ability to have a deterministic low latency interrupt delivery mechanism, as well as being able to do this within a lightweight architecture. So again, you can't just make your interrupt controller half the size of your processor. So being able to do this in a sort of resource constrained way is important. So looking specifically at the interrupt delivery mechanism, what we've created is a sort of layer on top of the defined message signaling interrupt that we call direct message signaling interrupt delivery mechanism. So again, these are all optional extensions. So if you have, everything is backward compatible. So if a customer, is okay with the existing standard interrupt architecture, that's not an issue. It's fully supported. But here we now have this sort of extra direct message signaling mechanism where you have a deterministic latency. So it creates a separate bus that is a wide bus, and again, focused on the real-time determinism. Each of the interrupts can be configurable basically per source on the APLIC side. And you can prioritize that, whether it's by domain, whether it's the specific target, or whether there's a priority domain. So you can create that prioritization. And so this is very focused on each processor. We still support the sort of general MSI if you need to do interprocessor interrupts. So that's one aspect of it. The nested vector interrupts, again, there wasn't really support for nested vector interrupts if you want to have a prioritization scheme of interrupts. So we've added this extension, again, layered on top of the existing AIA, where we've added a vector table. And then within that vector table, we can have up to 255 high priority nested interrupts. And we can also support the lower priority interrupts as well in a vectored implementation. These can actually be chained together at the sort of bottom of the table, if you will. When the interrupt is complete, that's signaled in software, and basically the threshold of that table that we've added is basically updated when that interrupt is complete. So it's another area that we've recommended extending the existing AIA. Another area that we've made some recommendations is on the trap stack pointer management. So basically, the initial trap management was effectively stackless. So basically, by adding stack functionality within the trap architecture, you can reduce the context store and restore overhead that you need to provide that quick turnaround on context switching. It allows the hardware to actually automate the size of the trap frame, and these things are each runtime configurable, for each privilege mode. So it's supported for any of the privilege modes defined by the ISA. And it's compatible with all handling modes, whether that's direct interrupt architecture or a vectored interrupt architecture. And again, fairly simple, fairly straightforward, layered on top of the existing trap structure. And so what did we see? And if you look at that, we kind of, again, all of this is sort of being done within the concept or the constraints of a very tightly resource-constrained system. So most of these are embedded applications, and so you can't just have unlimited architecture and power resources. And so we did some analysis on what we're recommending and kind of look at how that's affected, or where do we see in terms of results. And if you look at, for instance, looking at the delivery mechanism itself, how many cycles are you adding by adding this type of functionality? Obviously, as you have in a, say, multi-core processor, the number of cores is going to exacerbate the latencies on an interrupt architecture. But you can see there, even at systems that extend up to, say, 8 cores or 16 cores, the number of cycles that we're adding for both the DMSI delivery as well as layered on top of the standard APLIC and IMSIC cycles that you need to run to process a single interrupt is fairly limited. So we're not adding hundreds of cycles in order to support this direct message interrupt structure. And if you look at the overall prologue in terms of the number of instructions that are added for, say, the nested vectored interrupt recommendations that we're making, you're adding just tens of instructions to basically support the nested vectored higher priority interrupts. Even the lower priority, chained interrupts that we're adding at the bottom of the vector table don't add a significant number of instructions to the overall calculation. And then from an area perspective, there's low overhead in terms of area. So if the standard IMSIC implementation is sort of normalized to 1.0, the amount of area that we're adding to support nested vectored interrupts is less than half of that. And then the direct message signaling interrupt architecture that we've layered on top of that is even less. And so you're adding significant performance improvements specifically around real-time implementations, but without adding a significant number of gates or costing a significant number of additional instructions or cycles. So to sort of summarize the areas where we believe that what we're providing around real-time interrupt architecture and how it enhances the existing AIA is kind of four areas where we believe it's important to have this capability. One, again, we've talked about is the real-time capability, being able to extend the existing AIA to support or better support real-time capabilities, to be both efficient and flexible. That is super important. Compatibility, again, as you all know, being able to maintain compatibility with the standard ISA for implementations that may not want to implement or need to implement this additional functionality is important. And then the ability to extend it as well. So we define a set of features today, but we want to make it flexible so that in the future, that can be extended. So on the real-time side, again, the DMSI, I would argue, is probably the biggest bang for the buck, so to speak, by having this direct messaging structure where all of the latencies are very deterministic around interrupts. And you can still have prioritization, flat prioritization over the interrupt sources that you're basically bringing into the SoC, whether it's external interrupts that may be, sort of standard interrupt architecture layered on top of this DMSI architecture. And then flexibility, so basically being able to support single core, multi-core virtualization, so it's flexible. It supports non-virtualized as well as virtualized architectures, and it doesn't cost any new CSRs. So that's pretty important as well. You're not adding overhead by additional CSRs. On the compatibility side, so basically it's supporting the same binary interface across all targets. So it's fully backward compatible with non-real-time, both the privileged ISA as well as the standard RISC-V ISA. And then this aligns to how AIA approaches virtualization. So we're not inventing or reinventing the wheel here. We're effectively supporting virtualization, but more in a real-time environment. And then from an extensibility perspective, basically, we're providing the capability to be able to extend that architecture. So from a software perspective, being able to leverage existing software even as the RTIA is extended, that's super important. So basically, if overhead and compatibility is not critical, then there's this ability to have room for future expansion. All right. So I think that kind of covers it in a nutshell what we've proposed. And again, these are custom implementations or extensions that we're building into our products, but we're also in the process of basically bringing this to the RISC-V standard as well. Ideally, I think this would be an extension of AIA to support real-time on top of a sort of standard or say host processor types of implementations. All right, I guess we have time for a couple questions.
Yeah, thanks for the great talk. So for this real-time extension, do you also consider the security issue here?
Yeah, there is. So we are kind of looking at that. I think the original thought process was let's focus on just the sort of functional side of it, basically driven by customers. But yeah, we have our security team also looking how that sort of layers with the security side of things, world IDs and sort of the idea of the different domains and privilege levels within, say, an MPU architecture. But yeah, we are looking at that as well.
Could you draw a comparison to the fast interrupt work that's happening?
So I think that if I understand it correctly, and I'm not an expert on, but I believe that our team did or has been working with the fast interrupt team. I think the goals are a little bit different. I think if I understand it correctly, the fast interrupt goal is to basically really look at making sure that there's a sort of low lightweight architecture that supports sort of like smaller embedded types of applications. That's where we originally were bringing this RTIA. I think the fast interrupt team is sort of already moved to the point where they're ready to ratify. And so I don't know that it's going to fit in that context, but I would say it's a little bit orthogonal to what's going on there.